Welcome everybody to the second day of the first International Rock Mass Classification Conference. We have had a very nice first day yesterday. We had intense discussions, we had very interesting and I think also important discussions. We talked about the future and critiques of rock mass classification systems in the morning, and then we continued with digitalization and modern technology in rock engineering and rock mass classification in the afternoon. Today, right now, we have a very special part of the program, which is a scientific farewell for Dr. Evert Hoek. Dr. Evert Hoek, he passed away this year in July at the age of 90. And I'm very well aware that in the field of rock engineering and also rock mass classification, there are, let's say, mixed opinions about this work, as there are about all of these systems. But I think there is no doubt that the work of Dr. Hoek had a tremendous impact on the world of rock engineering, and it absolutely shaped what we are doing today, the way we think, and also what we discuss here at this conference. And so in summer, the president of the International Association of Engineering Geology reached out to us because he said, Professor Vassilis Marinos, he said that he thinks the RMCC would be the best or a very good opportunity for a scientific farewell for Dr. Hoek. And we all found this proposal very interesting, very good. And therefore, we then arranged this scientific farewell, where first of all, we will get a presentation of the biography from Dr. Hoek. This will be presented by Professor John Harrison. Afterwards, there will be a presentation from the president of the International Association of Engineering Geology. And lastly, there will be a presentation of the representative from the International Society for Rock Mechanics, from Professor Leandro Alejano. Also, you might notice that we have some cameras here, and the reason for that is that we said this is an important thing for this conference, that it is a nice addition to this conference, and you, as the audience, you have the chance to participate here live. But also, we think that this scientific farewell is important for the rock engineering and engineering geological community worldwide. That's why this part of the event will be recorded. We will then edit it, we will compile it later on, and it will then be presented on IAEG's, ISRM's, and NGI's YouTube channels and other social media channels, I suppose. So just that you don't wonder, if there are questions in between, we will edit this out. So feel free to ask and comment, of course, however you want. With that, I want to say, let's get this started, and I give it over to John Harrison.
Thank you very much, Mr. Chairman. Colleagues, I have an impossible task before me, and that is that I have to summarize somebody who has had a 60-year career in rock mechanics and rock engineering in only about 15 minutes. So I will try my best. It obviously is going to have to be an idiosyncratic view because I just simply cannot cover all of his work in that time. I think many people will know that Evert was South African. He was actually born in Zimbabwe, which at that time was known as Southern Rhodesia. But probably not what many people know is that he was actually a mechanical engineer. And I've said that he was a pioneer in rock mechanics and rock engineering, and a pioneer means one of the first people, and he genuinely was. He was a mechanical engineer because at that time, that's all that existed. And he did his first research at a place called the National Mechanical Engineering Research Institute in South Africa. And we'll see this photograph of Evert later on. And he produced a report in 1965 for the Institute, which I have called a tour de force. 237 pages. Now, of course, I'm not expecting you to look at this report, but that's what you need to know. That's the title, and you can see that it was 1965, and it was produced as part of the Council for Scientific and Industrial Research. And I'm now going to draw some things from this report because I think they're very, very interesting for us as a retrospective. It says that the study is presented in 3 parts. And when one sees a report which is structured like that, one immediately starts thinking, this is a PhD thesis. And I haven't been able to confirm whether this was Evert's PhD thesis or not, but I strongly suspect it was. And we can see that he looked at 3 parts. Theoretical considerations, essentially based on Griffith theory, and then he did some laboratory work and then also looked at engineering application. I'm not going to look at the theoretical considerations here. I'm just going to concentrate on parts 2 and 3. And this is one of the images from this report. And it's a plot of rock strength, what we would now call peak strength. Horizontal axis is the confining pressure, vertical axis is the axial stress. And importantly, when we look in one small part of the vertical axis, we can see something which I think we can regard as a hallmark of Hook's work, and that was normalization. And so we can see here that he was presenting the axial stress results by normalizing them with respect to the uniaxial compressive strength. We regard this these days as just common practice, but at the time, Hook was doing this as a means of trying to tackle the problem of the fact that all rocks were different. Something else which is worth looking at is that every single data point on this plot is labeled. So there is absolutely no doubt as to which rock and which test those points apply to. And I think that's something that we seem to have forgotten, that these days we tend to produce plots and it's quick and easy for us to do so. There is many software packages that will allow us to do that. But we forget the simple things like make sure that people can actually see what the data are. The next nice thing about this plot is down here. So this is not just a plot of compressive strength, this is tensile strength. And in 1965, how does one undertake tensile testing of rock? Well, the simple thing is you design and build a cell that will do that for you. And so here we see the dog bone specimen, which many of us will probably talk about in our teaching, having never seen one and having never actually done the test. But here in 1965, or probably 63 or 64, Evert Hoek, as a mechanical engineer, was designing these cells which would allow him to undertake a tensile strength test. And I think it's important that we recognize that Evert Hoek, not only was he doing pioneering research in terms of obtaining the data, he was also doing pioneering research in terms of developing the equipment. And we mustn't forget that when we perform triaxial strength testing, we are usually using something called a Hook cell. And it's called a Hook cell because he was instrumental in its development. Let's carry on, and let's pick at something else from his report. Once one has set up the equipment to undertake triaxial testing, then there's all sorts of things you can do. And so here we have probably one of the first reports of the triaxial strength of anisotropic materials. Behind this, there is an analysis based on the Griffith criterion, but I don't want to talk about that. I just want you to see here, again, he's presenting his strengths in normalized form. Here he is normalizing with respect to the unconfined compressive strength, which is perpendicular to the fractures. And we have the angle of inclination of the fractures on the horizontal axis. And so he was confirming the well-known U-shaped curve that we have for the strength of anisotropic materials. And he didn't stop there, he moved on, because he was very interested very interested in the stresses that were induced around underground excavations in rock. And so this is one of the images taken from this report. And this is a physical test to determine the major principal stress induced around a circular opening which has a crack in both the roof and the floor. So I've highlighted the cracks there, and this is then the distribution of stress. He obtained this distribution of stress using photoelasticity. So we have to remember that this predates almost all computational techniques. And so this was physical testing, analog testing, where he built a rig which allowed biaxial testing of underground or circular openings using this material called photoelastic layer. And for those of you who have never seen a photoelastic rig, it looks like that. And so somewhere in the middle of all of that is the experiment, and the rest of the equipment there is to generate polarized light and then record on a film camera. And so let's look a little bit more closely there. And so this is Evert Hoek standing in front of his equipment. We can see the polarizers. At the left-hand side, we can see the camera on which his results were recorded. From 2024, that looks like an ancient bellows camera. But of course, at the time, in 1964, that was a bellows camera. There was nothing ancient about it at all. And so this is this is the earliest photograph I have seen of Evert Hoek, and this is him as a man in his early 30s. He was a man of his time, so we probably wouldn't stand dressed like that in a laboratory these days, but certainly that's what one did in the 1960s. He left the CSIR in 1966 and moved to Imperial College in London at the Royal School of Mines. And this is where I first became aware of this fellow by the name of Evert Hoek with these two books. I literally took copies of Rock Slope Engineering and Underground Excavations in Rock last week in order to prepare this. And I think it's fair to say that many people, certainly of my age, will regard these two books as setting rock engineering on its current path. And there are many people in practice who still turn to rock slope engineering and underground excavations in rock as their key texts for their work. Both of these were developed at Imperial College as part of a very large research program, and they are indicative of the efforts that Evert made to disseminate his results to a wider audience. He left the Imperial College in 1975 and moved into the geotechnical industry. So he was working with Golder Associates at Vancouver, and so he'd moved from South Africa to Britain to Canada by this stage. And in 1987, he then moved as professor at the University of Toronto, and he was only in the University of Toronto for 6 years, 1987 to 1993. But it was during this time that I first met Evert Hoek. And he gave me a 3.5-inch floppy disk, and he said, try this. And on it was this program here, Examine 2D. And I was astonished that, first of all, it was possible to produce a boundary element program that would run on an IBM PC, and secondly, that he would be giving it away. But from that early work, the company Rock Science was developed and has now grown into one of the largest software developers in the field of geotechnical engineering. He didn't stay at the University of Toronto long, and I don't know whether that was his choice. I do have some idea of what was going on at the University of Toronto at that time, but for whatever reason he left. and he returned in 1993 to industrial practice as an independent consultant. But that didn't stop him disseminating his results, and so even today you can obtain a copy of this thing called practical rock engineering. And I call it a thing because in the foreword, Evert says it is not a textbook and it will never be published as a textbook, but you can obtain this from the Rock Science website. And it's essentially a distillation of everything that he learned over the years in practice. Now that's everything that he did, but there is something else that I want to draw our attention to, and it is this. And so in 1992, the ISRM began publishing the ISRM News Journal. It was an initiative of the then president of the ISRM, Charles Fairhurst. And this was published and delivered to us in paper form every now and again. I can't remember how often. And if you want the links to these news journals, and I encourage you to do so, here's the QR code. And I particularly want you to look at volume 2, number 2. Because in that, there are 2 contributions from Evert Hoek. And I've called this part of the presentation a cri de coeur, because I think that's what one of these contributions was. The first one, I'm not going to pay any attention to today because I know that my colleagues will do so later, but it was a paper on the strength of rock and rock masses. And if you read that now, you will see it's very familiar material. But what I'm interested in is his letter to the editor. And I remember reading it at the time and being astonished, and having reread it in the last week or so, I think it is still a very salient point to be made. The challenge of input data and rock engineering. Now we have to remember this has been written by an engineer who at that time was probably about 62 or 63 years old. He'd spent an illustrious career in both research and industry. I think he was of an age where he felt that he could say what he wanted to say. And what he said was this, and I'm not going to read any of these because you can read them far faster than I can, but he was concerned about our ability to collect and use geotechnical data. And when he refers to a time not too many years ago, he's referring to probably something like in the 1980s, before we had desktop computers. And it was very difficult for us to do analysis. But now he says things have changed. And we're now faced with severe data limitations. He was concerned that we had terrific software, but we didn't have the data to support them. And he accepted, or he understood why we had these problems. And so he picked on in situ stress as an example. They give an amount of scatter which would be unacceptable in almost any other branch of engineering. Don't forget, he was a mechanical engineer, so he knew about other branches of engineering. And this is still the case. When we look at in situ stress data, they have scatter which would be unacceptable for any other branch of engineering. And he recognized why this was the case. It was heterogeneous nature of rocks. But then he posed a question. What are we doing to try to understand improve our understanding of these problems? And he said this, the answer is very little. And I think he was in a position in his life that he could say that. And I'm sure that this angered quite a number of people at the time. He then took a swipe at the research community, and he said that there was very little effort being done to generate basic input data. And thinking about this, I still agree with him. We know that we have techniques which will allow us to gather some basic input data, certainly associated with rock mass geometry, but there are still areas where we are not able to obtain our basic input data. And he was recognizing that we needed these for numerical models, but also for improved design techniques. And at this time, Hoek was using computers to undertake probabilistic analysis and realized that he genuinely didn't have the data to do that. And he says these tools are rapidly reaching the point of being severely data limited. He was very concerned that we were buying these very sophisticated software packages and having no data. And the data that we were using, we were essentially inventing. And that's what his major concern was. The second page of his letter, it was more of a monograph than a letter, he makes these points here, and I think that Leandro, who follows me, will probably mention some of this as well. So when he and Ted Brown were writing underground excavations in rock, they realized that they had a gap. And having spoken with both of these authors, I can confirm that they both have this view. They didn't have a strength criterion, and so they had to invent one. And as we can see here, they had limited data of rather poor quality. I suspect it was that they didn't really know the provenance of the data more than anything else. But he's talking about the development of the Hoek-Brown strength criterion. Very limited data, rather poor quality. And he then says they offered this as a temporary solution to an urgent problem. So it's important to recognize that in the late 1970s, Hoek and Brown were thinking just in terms of it being that. And then Hoek says this, he's alarmed, or he was alarmed in the mid-1990s to see the criterion being applied to problems that we did not even dream about. And then he describes their work, desperate estimates. We sit here believing that the Hoek-Brown criterion is something fantastic, but Hoek himself regarded it as a desperate estimate. The fact that the criterion works more by good fortune than because of its inherent scientific merits is no excuse for the apparent lack of effort or even apparent desire to find a better way. This is what he was saying in 1995. Here we are 30 years on, and I think we should ask ourselves, have we tried to find a better way? And so I'm going to end by saying this, that I think we should try and honor Evert by seizing his challenge to find a better way. And with that, I will finish. Thank you very much.
Thank you very much, John. And we move right on to the next presenter, which is Professor Vassilis Marinos.
Good morning, Mr. Chairman, ladies and gentlemen. This is a great honor for me being here today. First of all, I would like, from my side, before giving my farewell as President of IAEG to Dr. Evert Hoek, to say that we thank you very much for organizing this conference in rock mass classification, and NGI for hosting this event. So we're really thankful for that. I had the pleasure of being here as a student 25 years ago in the summer, so I really have in my heart NGI, and it is a really pleasure now giving from this post right now this farewell for Dr. Evert Hoek. I have to say that we are one of the two missing papers in your slide yesterday with Carter Trevor, who is in Antarctica right now, so we are missing him. His presence here would give a great contribution to this conference, but in any case, I wanted also to acknowledge that. So our presentation will be about reliability mastering, rock mass strength estimation using GSI. So we're not going to highlight the Hoek and Brown. Of course, we're going to link it with the GSI, but we're going to focus in, yes, on GSI, but in general, Evert's contribution to engineering geology, but also to rock mechanics. So this is an outline of presentation. I have to say that if you have listened to Dr. Hoek's presentations, they were very plain. Not a lot of slides, simple slides, so I'm not gonna do that. It was his way of giving the presentations. I'm gonna have the other way, honoring him. So I have a lot of work here. Of course, I want to run many of them, but since this is recorded, I wanted just to have the slides running in some cases, so this can be available to everybody. So the first thing about, the first part, of course, is about Dr. Hoek. So let's see. We have seen that slides, so I'm not going to repeat that. Yes, we keep that he was a mechanical engineer, and all the evolution Professor Harrison gave us, so I'm going to run this. But you also, apart from the evolution and notes, same Dr. Hoek made, I wanted also to add some distinctions. Of course, he had all of them, actually. And of course, these contributions in the books we all read, and our students read, and definitely what he worshiped was that, okay, he left the academia to go into consulting business and try to give answers to questions. So it was very important to him not raising the questions, finding the gaps that we all make in here, but giving the answers to that. And this was astonishing, but mainly to disseminate this, to communicate. This was a way in communicating with the people all over the world. And I remember his notes saying that a good day to me is when I have responded to all the emails before I go to sleep. So this was very important to him. So Hoek's Corner in Rock Science is a fantastic digital library with many case studies, not only the principal, the same selected papers, and of course practical rock engineering. And he has made many video lectures, and many of them sum up his contributions the last years of his life. I remember emailing to him, and he was really devoting a lot of effort, a lot of time in this late age to how to make a perfect presentation in his eyes. So in order to deliver one of these video lectures, you have to understand that there is an enormous effort behind that. Every slide has had a lot of time spent in order to deliver to all of us, and is as a heritage to all the future generation. So, putting numbers in geology. This was a milestone from our side as engineering geologists, but before going to that, we have to step back a little bit and see where we stand here. That ISSMGE was born in 30s. ISRM and IAEG came about 60s in the geoengineering triangle. So we settled that 60 years ago, around 60 years ago. But this is a constant effort of how we work together and why engineering geology matters in rock mechanics, in soil mechanics. And of course, this was established by the works, by the problems themselves, by the failures, by tragic failures. So tragic accidents and natural disasters brought the necessity of how we describe the geological material, connect it with the geological processes, and how we can differentiate and how this variability that is dictated by the geological history can affect our design and construction. So this is actually when we became important as engineering geologists. But Dr. Evert Hoek not only respected, let's say, the geological knowledge for the engineering problem, but tried to incorporate it through GSI. So he saw a gap in all these characterization of how the geological differentiations can be also acknowledged. So this was a principal contribution for that. And as an engineer, as a mechanical engineer, of course, then appreciated as a rock engineer, was an advocate of geology. So we are really very thankful for that. And he delivered the prestigious Glossop Lecture of London, pushing ahead geology to engineer, putting numbers, geology to geology. We're going to see some more about that. So we know that right now engineering geology contributes through the ground profile, through predicting the ground behavior, and try for a realistic model to be analyzed. And we are also thankful to Berland's triangle for that, because everything that comes from engineers into the world, highlighting the importance of the geological contribution to that, it's founded better in the conversation. So we're really thankful for that. And we know that we had to translate from the scale of the mountains to the scale of the project, and then distinct the ground types and go into and assessing the failure modes, selecting the suitable parameters for any analysis, and then proceed to the design construction, and of course monitoring, validating all our design. So this is the path of our work, and there the rock mass classifications contribute a lot, but we're going to see about that. So as geologists in engineering problems and in rock engineering design, we have first to determine the rock mass, the ground profile, the geological model, quantifying the characteristic, putting numbers in geology, and then determine the failure types, determine the design parameters, and then analysis and dimensioning of the technical project is something that we help. So the conceptual part. Of course, so when the design parameters come into play, then we work a lot with the engineers of the problem to select the critical ones. So the realistic model comes to that, the realistic failure mode comes to that also, so this is very important. You can read there, I have put it in the next slide. I just wanted to stay in this one and say that a milestone in Dr. Hoek's work in the GSI and using geology in his work was the collaboration with my father, Professor Paul Marinos. And we had big projects in Greece, Metro of Athens, very big highway of 700 kilometers under critical, very difficult geological conditions. And this was a milestone of finding, let's say, problems that we couldn't characterize normally, so best estimates and engineering judgment was the best we could find and try to help to assist in the design and the construction. And this is a picture 10 years ago. I was very happy doing a sabbatical in Canada, so I had a road trip with Evert for 4 days in the Rock Mountains. It was the days that was the period when he lost his wife, his first wife. So this was a fantastic trip. You can understand in the Rocky Mountains, discussion about rock engineering, about GSI. It was one of the best moments of my life. So here is something to remember. So what he states in this Glossop lecture, of course, speaking to geologists, mostly and engineering geologists at that time, if we can quantify the geomaterials and striking a delicate balance between the opinion that geology cannot be quantified from one point and the over-optimistic view that every physical entity can be described in mathematical terms. So in reality, many geological features, as we understand, cannot be precisely quantified in parts of the world. So today, this requirement has been met to a remarkable extent with the development of engineering geological research, mainly, yes, new equipment, field tests, laboratory, and remote sensing tools, and the geotechnical classification system. So we have shifted our efforts to that. Of course, I'm going to also criticize and make similar points like Professor Harrison made in some minutes. So we understand that geological representative is key to achieving effective rock engineering design. So despite the fact that we have significant advances have occurred in almost every area in geotechnical design, we arguably the greatest development in rock engineering being in numerical modeling. To date, similar levels of advance has not been achieved in improving characterization of the geological variability. So we all saying the same things, but we try also to, in the meantime, still we're going to research and we are going steps forward to give answers and to assist the design and the construction of real works. So we require that reliable estimates be available of strength deformation characteristics of rock masses. So Dr. Hoek tried to fill that gap, of course, with the big contribution of what you saw and presented by Professor Harrison. So here in rock mass properties, we cannot have laboratory testing for rock masses. We can have, though, for intact rock masses, definitely, and this is an area where we are not doing a lot of work, also in the design, in situ testing, the scale issue problem, also budget issue problem. Back analysis, of course, is the best way to estimate these properties, but you need a failure or you need a deformation in order to proceed to that. So the use of rock mass classifications is vastly used for the estimation of rock mass properties. So rock mass characterization and classification is a vehicle in translating this geological variability into an engineering structure. So I have put here some complex and not straightforward rock masses, as some of you may have worked with. But we need to understand that this rock type, this rock mass type, so from the intact rock to the rock mass, right now, we have to see the genesis reflected in the quality of the intact rock and inherent structure, anisotropy sometimes. The tectonic evolutions reflect on the rock mass structure, fabric, and quality of joints. And of course, paleogeographic evolution reflects on weathering and final fabric. Of course, metamorphism and alteration are some other effects. So with the development of these extremely powerful computers, engineers required input data. So the Hoek and Brown came there to assist, and also with classifications that gave some, for tunneling mainly, solutions of how we can support our rock mass. So the necessity led to the development of a different set of rock mass classification, and the geological strength index is such as a classification. So let's go to that and see some evolution of the GSI. So you all know that 1994, Hoek introduced GSI index. So, but in his equations, he mainly used something that the people already knew, which was the RMR a lot. So he selected to put the RMR in this equation. But then in 1997, Hoek and Brown published a GSI in the form of a chart with a new rock mass classification system. This is not the current form. So GSI now replaces the RMR as an input data in the Hoek and Brown criteria. And then his synergy with Professor Marinos in many projects around the world resulted to this chart, which is the Hoek and Marinos 2000 chart as you know it right now. And of course, different evolutions contain the heterogeneous chart with the competent and incompetent rock masses, so tectonically deformed rock masses. Of course, there are updated, revised versions, but this is not the point of this presentation, not to stay in the GSI. And tectonically undisturbed also sedimentary series. So the estimation of rock mass properties, once the GSI has been selected, then the system becomes highly quantitative, of course. And GSI can be used as an input into numerical analysis and closed-form solutions. So at that time, always Dr. Hoek wanted to highlight again and again that the GSI is not intended as a replacement of RMR or Q, It has no rock mass reinforcement capability. Its only function is the estimation of rock mass properties. Of course, I will add, as a practitioner of GSI and author of many papers with Dr. Hoek, that also GSI is used for the rock mass characterization. So this is a Hoek and Brown failure criteria. Of course, I'm not gonna speak about that. Leandro is gonna speak about that. But we can see that this is a flow chart in a paper of Hoek in 2013, how we use geological observations, so visual chart or a quantitative chart, and then we go into the Hoek and Brown together with intact rock parameters from laboratory testing, and then we reduce the strength through the Hoek and Brown criteria. And then, depending on the in situ stresses, groundwater, damage factor, excavation sequence, so we can analyze that all sequential and analytical, so we don't need to penalize it through a rock mass classification. We can do it through the softwares, so numerical analysis of overstress and remedial measures. And then, of course, a verification and modification comes through in situ monitoring and back analysis. And all these are attempts to quantify GSI classifications, and we're gonna see over the years many papers. Every 1 or 2 months we receive papers for review, somebody correlating classification systems, the one with the other, or try to quantify that, because we understand that engineers are very comfortable with the numbers in order to reach to a classification value, but the main competence of the GSI is the geological strength index. So I'm gonna focus on that here today. So you see all this running, these quantified charts we have in the literature, and they probably because the same authors felt that this is the best way for us to solve a problem, or for a research, or for a PhD, or to develop, to find the gaps, to find the limitations. So you see all these new graphs and new equations in order to quantify the GSI. So I had to put that. And to the question that was made yesterday, I think to Elmo, that was about the veins. And this is a fantastic work by Jen Day from Queen's University, Day, Didris, and Hutchinson, how they really evaluate this sealed. I think that this question was made by you, or no, by Professor Mercer, about the veins. So this is a job focused on sealed joints through veins. And the same quantified material Hoek et al. For 2013, together with Trevor Carter and Didrix, and some other quantitative charts here. So I'm not gonna stay in detail about that. And this is, I think, the most recent one. So we go back to this basic chart, which has the structures as you know it. So you need to identify the structure of the rock mass, and then the surface quality, the surface conditions of the rock. And you do that from outcrops, you do that from borehole drillings, you do that from face mapping or for excavation during construction. But the main issue also when you classify, when you use this GSI or any rock mass classification scheme, is to think about the scale. So this is a very well-known scale effect. So apart from how you detect the ground type, depending on lithology, tectonism, weathering, alteration, and then when should I change the GSI value also depends on the scale of the problem. So I'm not gonna speak about that. So you may have an isotropical failure when the GSI may not work and the Hoek and Brown should not be used, and on the other scale that this can be used because it is within the limitations the authors have developed that within the range of application, sorry. And I remember I was in an outcrop in Greece with my students in a field work, and my father and Evert, they were making a holiday in northern Greece, so they knew where I was, and they stopped for 1 minute, and I said hello, and I said, I'm just describing why the students should not be using GSI here. So it was, and he made like that, and he left afterwards. So I'm gonna come back, some comments about that. So we have on one side the intact rock parameters from, and then the factor is reducing the strength of the intact rock with the GSI and the disturbance factor. And of course, this is the ID, the numerical ID for an isotropic analysis, of course. So if you want to use these numbers for the Hoek and Brown, you have to be sure that you have these numbers. What we get right now, so I strongly agree, is that many companies, they require very fast numbers. This is a very stressful situation. Somebody to give fast some rock mass classification numbers and some uniaxial compressive strength and the laboratory and MI values, so nobody does a triaxial test. And for example, I asked a very huge project, how many triaxial tests your companies, design companies that had the projects, the contracts, and they said none. So they are just relying on the table, some other, and like that, Hoek and Marinos from MI values, and they don't perform triaxial tests. So we try to do it, and my PhD students, they really sweat a lot in the laboratory making all these triaxial tests in order to publish and have at least these variations. And you see these variations, they are huge. So in order to just select one number from a table, it's totally wrong, and as Professor Harrison already highlighted. I just wanted to show on the right corner how the different rock mass of the bubbles you see in this GSI chart, which are for different rock mass in geological environment, with the sigma CI NMI, they can have a lot of combinations due exactly to the geological variations we have, not only because the nature of the rock itself, but its geological history and the intact rock properties. And of course, the empirical relations connecting with the deformation modulus. Again, all these are used in practice, in the design, when I say in practice. And this is a GSI as a tool to characterize, and if necessary to classify, if we want to use this number into any form of analysis, numerical analysis. But I wanted just to show how we use that in Athens Metro in Greece. So we have a very complex bedrock below Athens. So we have an Athens schist. We have the upper unit and the lower unit. This is a tectonic nape pile during alpine folding and thrusting. So we have alternations of rock types of variable strength, deformability, and durability characteristics. So here, Professor Hoek, when he came as a consultant at the end of the 90s, he was watching rock masses that he hadn't worked in the past. So watching all these rock mass types, and you see the upper unit, which is fractured and disturbed, but okay, and then going to something which is very sheared and foliated with a lower sheared unit. And you see all these different kind of materials ranging from blocky to very blocky to brecciated, because mostly there are meta-sandstones, so they have more brittle behavior. But below that, due to the thrusting, we have the black schist, which is from blocky disturbed to semi and foliated. So all these should be somehow characterized and should be somehow evaluated for its behavior in the TBM machinery, and of course analyzed in order to proceed with the construction. So it was a real problem. Requires solutions, and of course an expert then at that time, a consultant, could help into finding that. So this was a new challenge. It wasn't something already published. So after all this description, which is geologically based, then we have all these intact rocks, and we have the GSI system try to quantify, and we have these bubble charts to see the differentiation between one section of the tunnel. And then, of course, we have combinations of the GSI in these sections with the depth, but also in the horizontal, and then laboratory tests with uniaxial compressive strength and correlating with the deformation modulus of intact rock. And then all these previous geological, nice conceptual, because this was mainly conceptual, of course, based in some boreholes, because this is in FID, this is in tender documents, so it's not yet, let's say, added with new boreholes. So we can have this translated by zone, specific rock mass types with numbers behind that, some numbers that are characterizing a ground type, or numbers that we can or we may use in any sort of analysis. So I'm going forward to how the GSI can respect the engineering geological characteristics and how tectonism reflects on rock mass characterization, how weathering and how alteration reflects on rock mass characterization. So how geology cannot be bypassed by putting numbers, but following, eventually we need to put numbers, but we need also to follow the process. So depending on the severity of the tectonism and how the rock mass can be deformed to something which was blocky and then it's brecciated or foliated, of course depends on how brittle or ductile is the material. And if it has also heterogeneity before, then you may have some more mixtures in your problem. So you see the path of how tectonism can change the rock type. So we see here, for example, this is an engineering geology model in a fleece environment. So we know that fleece is not a rock, it's a formation, and it is almost everywhere in the alpine belts all over the world. So we have alternations of a competent and not competent material, and then within a few hundreds of meters, we can have all these rock mass types. So these rock mass classification systems, they first help us in order to distinguish this rock mass, the changes in rock mass. But imagine in this stretch of the tunnel, we may have only one borehole or two boreholes. So in order to differentiate and say I have 6 ground types, you need a very well appreciation of the geological model all over the area. So you need a very good mapping, and you need the classification system to guide you of what kind of variations you may have next to that borehole that you don't have data. So this is very important to identify how the complexity of the rock mass or how weak a rock mass can be due to the structure or due to the tectonic evolution or due to the presence of clay formations, how they behave in brittle or in plastic deformations. So you need to understand that all these rock mass classification and characterization in this case assist us. And for example, here, this is one of the most difficult tunnels because we have a big thrust from one fleece unit to another fleece unit. So we have a mountain that traveled hundreds of kilometers to go there and built in a tunnel, only 90 meters overburden. But this was a very difficult one because you had the satellite thrust. So you need somehow to differentiate and appreciate how this rock mass can change within the tunnel and how you can assist, of course, in the supporting one. So you need somehow to distinct how much rock mass types you can have. And then from the knowledge, first, you have a base, you have a Hook and Brown, you have a GSI chart, and then you say, okay, I have results. I have a construction, I have a design. So after building tunnels, for example, 15 tunnels in this kind of environment, then you have some data. So you can help the following projects in this kind of environment and say, okay, you can appreciate that you may have these 11 types. And these are some indicative range of values that you can use if your rock mass behaves isotropically, because many of them behave totally anisotropically in many cases. So your problem is not through Hook and Brown and GSI, etc. And you see some pictures of how all these shifts towards the end to the lower floors of the GSI, depending on the fracture and tectonic mixtures and foliation. So the same rock mass like that could be in the next tunnel phase as a blocky one. So you put numbers, but you definitely need to know if you have an isotropical failure squeezing, so you can put this, you have an overall failure of the rock mass. So in this case, okay, I can use a Hook and Brown criteria, safer, and estimate the deformation along the tunnel. So for this rock type of the picture there, in the 50 meters, in the 100 meters, in 200 meters, 500 meters, this is a kind of problems I may be facing in squeezing. And this is a more recent project in Romania. This is a big TBM tunnel, so you need to then, of course, identify the intact rock properties, of course, of the different rock mass types. you have the lithologies, but then you need to identify all the ground types you have. So from using a classification scheme that can help you and putting not just numbers, but try to assign what you expect on your tunnel phase, and then put the ranges, and of course, not only numbers, but a range of values, because this is an empirical relations. There is no point of saying that the GSI is 28 or 28.5, etc. So you need to provide a range. But before assigning all these numbers to every ground type, the next step, before using, not assign, before using these numbers, the next step is to assess the failure mechanism. And then, after you assess the failure mechanism, here you see a chart after 70 twin tunnels in Greece that we have in different kinds of rock mass types and in situ overburden. So after you have identified for every ground type within your tunnel, within the in situ stresses and groundwater regime, you need to find the possible behavior types. We had yesterday a fantastic also presentation on that in TBM selection. So you see that in practice, how we did that in this case. And then you connect that with the geotechnical unit. We haven't used GSI yet. We haven't used any rock mass classification. We use our engineering geological insight first. And then if we want to see which kind of numbers they can help us in order to quantify the problem in some cases. Yes, then along the chainage, we can see in these different ground types, so you see these different levels, how much squeezing we may have predict along the tunnel. And of course, the mixed ground conditions that we may have and how they can dictate the TBM selection. And then, 2 minutes? So I'm going to pass this one. This is a pipeline. So how we use the GSI in order to change the rerouting, because the pipeline industry also requires in a few months a decision on why to reroute a pipeline. So in order to do that, we needed some questions fast. So with some boreholes and laboratory tests, we needed some numbers in order to provide together with Mark Lee, who is the next Glossop lecture speaker, to then decide which kind of landslide is risk or not. So how weathering reflects, of course, again, this is another now mechanism, and how this differentiated by foliated structure, tectonic disturbance, weathering degree, or the presence of shear zones. Mr. Chairman, can I have 5 minutes in total? Thank you. So you see here how the weathering degrees can reduce also the index rock, but the appreciating the rock mass strength. So these charts, these tables, are not for a practitioner to take this ratio and put it in the equations. Is to urge the practitioner that, you know, you have also this problem. Apart from the GSI, you have also to appreciate the index rock parameters. So in order to evaluate that, we suggested also in this high weathering profile, so when we shift from moderate weathering to completely weathering to highly weathering profiles, then the GSI dramatically reduced. So these surface conditions should be replaced by the weathering degree based on the ISRM levels. And then how alteration reflects on rock mass characterization. So you understand that here, for example, in a phonolithic complex, so how moderate or severe an alteration can be, you can follow these geological rules and the path and say, okay, between this one, I can have another type if I understand the geological history behind that. So we see here, for example, in ophiolites, that yes, the ophiolites is a complex by its genesis, as you saw before, but also through thrusting. And we have all these deterioration of the rock mass quality due to serpentinization and, of course, the tectonism. So we have originally compact, relatively soft, and more easily sheared by tectonic processes. We have, again, complex and weak rock masses. So you can follow this arrow and say, okay, I can have a rock mass type 1, which is very solid, and numbers of GSI and sigma CI. But then I can have something which is serpentinized along the joints, not in the rock mass, not to the intact rock, But then we have a change also in the intact rock strength due to the serpentinization, and the rock mass quality also deteriorates. So these visual charts, they help us in order to understand and link, let's say, in our geological model, how we can have these differentiations due to alteration here. So you see how the GSI changes, how you see also the uniaxial compressive strength, and the MI towards the last case where your rock is totally foliated. And this is not only due to tectonism and weathering. This is due to serpentinization during the crystallization of the magma. So it can happen everywhere in your tunnel. And this is a yielding support system in 600 meters in one of our most difficult challenges. And very high, very big landslides in this kind of material, as you see here in ophiolites. So, discussion. Somebody says, okay, discussion, so he closes the presentation, but I see 20 more slides here, so I'm gonna close that. So the discussion, this was when I was in Imperial College and totally loved the time. That was a Friday morning, watching Professor Harrison in these very nice blocks of charts in rock and how we can understand. But also my mentor in engineering geology, apart from my father, Professor De Freitas, he gave me an assign for, I remember, in presenting about the rock mass classifications. And he was provoking me because he knew that one of the authors was my father. So he put me in this position. And this is, of course, that the rock mass classification should not be used as a cookbook. We all know that. But here, this is an example how two different rock mass types can have exactly the same GSI value, so exactly the same intact rock type, exactly the same tunnel overburden, and exactly the same RMR values, and have totally different behavior. So a classification value cannot be dictating, let's say, our approach, and can be used here, for example, in both cases, GSI and Hugen-Brown is out of, let's say, they are not dictating the support system, let's say. So yes, we can use them in an analysis and have a documentation in our deliverables, but they're not dictating the measures. So we need to appreciate first the behavior and then use these numbers. And this is a slide I got from Trevor last night. So you see that GSI and Hugen-Brown criteria is incredibly powerful through the MB, through the Hugen-Brown. I'm not gonna talk about that because Leandro is gonna speak afterwards, but here is a link of the range of GSI and where Hugen-Brown works well, and when we get to the lower end, to the squeezing conditions or the brittle conditions. So we totally change our perspective on how we're working our problem. And then we need to understand that if the approaches we apply associated with the appropriate factor of safety based on the degree of uncertainties are satisfactory, provided they are not erroneous, and we said that there is a good percent that they may be erroneous due to this variability, it is obvious why the geological judgment must be always important. But I want to stay here and say that this geotechnical classifications value, a drone, a geostatistical analysis, satellite images cannot dominate up in any other judgment and cover their works and tasks. I see my students, I see my PhD students, which they have listened again and again, how much time they spend in the field. And they take the drone, they take the LiDAR, and they take the boreholes, they give the numbers, they do a statistical analysis, and they're happy, they continue, but they are not suffering too much in the field in order to try to find questions, because at the end, we should be, our work as engineering geology is to able to answer how the ground works, and how we classify and quantify the ground materials. So we need to understand that Dr. Evert Hoek appreciated that very early in his career, in the role of engineering geology in rock engineering analysis. Even in more straightforward, like for example here in Norway, that you have more straightforward geological information. The geological differentiations can be these minor deficits of the rock can dictate a totally different mechanism. So please, I'm not gonna read about that, but I have to also put that especially a specialist in soil mechanics, rock mechanics, and engineering geology, how should be also taught. In conclusion, so I think we must all agree that rock engineers have to work with the limitations of available technology, and some of the most severe limitations are associated with the estimations of rock mass properties, definitely. And efforts to overcome that have resulted in this development of the GSI and the other rock mass classification schemes, and can be regarded as interim solutions, for sure. And these efforts has been in most cases useful, since there are few practical alternatives available. So you see here, for example, in slopes from a work, how much all these classifications are used in the GSI and the RMRQ, and in the tunnels, we showed that yesterday, so they are used in practice. But we need to understand that we need to validate all these by monitoring and check them till the time we can have these quotes. So Hoek and Marinos in Europe 2009 said that we look forward to the time when these numerical tools will allow us to at least calibrate better, if not replace some of the empirical methods, such as the GSI classification and the Hoek and Brown criteria that we use today. And after the personal communication with Hoek is that my long-term hope is that numerical tools such as the synthetic rock mass and its offshoots will eventually enable us to replace classification type approach, or at least calibrate these classifications. But it may be a while since these hopes can be realized. So you need to understand that Dr. Hoek, not to understand, but I need to share with you that where you are in the mountains with a room next to you full of designers, full of constructors, full of engineers, and you have a landslide, an active, and you need to decide, because you have a huge budget issue, and you have a tunnel with severe squeezing, and somebody waits from the expert to give the results. Dr. Hoek never relied on the GSI value of the Hoek and Brown. His first appreciation was to understand the problem, and the next morning, when he was coming in the breakfast, he has made a kind of analysis in order to prove his way of understanding the problem and how should be this solved. So he never came with a GSI number of the Hoek and Brown in order to solve this. He was a pure practitioner, but at the same time tried to balance that and to prove that through this kind of analysis. And you see, through an extensive, many times 10, 12 days in the field, watching all the problems every 2 or 3 months, this is the kind of documentation needed to be sorted out within 2 days. So this is something that, together with my father, they really gave that to all the companies, that at the end of any, let's say, a panel of expert issue, they prepared their final report at the end of this. So everybody was very happy. And this is another memory when they had a blackout after a storm, and they went in the parking room they opened the car engine and they plugged the computer. At that time, I was a student, and I was only lucky to take Dr. Hoek from one place to the other and talk with him. But now, as a president, I'm really honored to give this farewell to Dr. Evert Hoek. So this is our announcement after his passing. And thank you very much for your appreciation, Mr. Chairman. Thank you very much for this overtime. Thank you.
Thank you very much, Professor Marinos. I think this presentation demonstrated well how Dr. Hoek's work was infused with a high appreciation for engineering geology right from the start. Due to the advanced time, we will move right over to the next presenter, which is now a contribution from the ISRM, and the representative is Professor Leandro Alejano, who will now continue with talking about what happens then basically in the world of rock engineering and rock mechanics with the geological information that we just saw. Leandro, the stage is yours.
Okay, thank you, Georg, and Thank you for inviting me to be here. And yeah, I'm honored, and I think the ISRM as a society is honored to be here, contributing to this tribute to Dr. Evert Hoek. So I was invited to do that by you, and also in the name of Professor Sequan John, the president of the ISRM. Thank you for inviting us to be here. So when I was given the task to honor Dr. Evert Hoek, I think about what I've taken from all the things he has done, and decided to focus on two main topics, also to arrange with my colleagues here this morning. So I've entitled this talk From Intact Rock to Rock Mass Strength as first part, and then I will talk also about practical rock engineering approaches. So let's start with the first one, and I would like to put things a little bit into context. So the International Society of Rock Mechanics was founded in 1962, and one of the reasons to found out, as Professor Marinos has expressed, was a number of terrible accidents that took place during these years, including the failure of different dams, and also big mine accidents like the one in Coalbrook in South Africa. And those are the words of Professor Hoek, saying, it was important to try to better understand how things were going. And in fact, our organization, ISRM, was founded in 1962, and the day before it was founded in Salzburg, in a group of engineers led by Professor Miller. He has an interview in a radio station, and the reporter asked him, do we know the strength of rock? And he said, yeah, for a test in laboratory, yes. For a rock mass, no. This is why we need to determine, and this is why we need an International Society of Rock Mechanics. So in the very heart of the foundation of our society was the idea of how to estimate the strength of a rock mass. Something at this point was really difficult to do. So as well appeared there in the words of Professor Müller, you need to know this behavior as the first task to safely lay out and make construction able to give answer to the questions for the design of big engineering works. So, well, this is a picture taken from a book of Professor Mullin in 1963, explaining that, what was happening when a slope in a rock mass was in some way falling, but still they were not able to have an idea of what the strength of this rock mass is. So the big problem was to move from love to reality. That was the problem at the time, but based on, well, different failures that are still taking place every year in rock mechanics, probably it's still an interesting question to improve in our way to ask that. So to try to understand how Professor Hoek, of course, together with Evert Hoek, get to the, well, first initial solution of their equation that was in some way answering this question, I basically refer to a paper by Evert Hoek in 1983, where he, well, first posed the problem. So he said that for jointed rock masses, an evaluation of shear strength presents formidable theoretical and experimental issues. And also he mentioned that it was absolutely important to look into the geology. So he also summarized what was known about the strength of jointed rock masses at the time, and explain in some way how do they get to this to their final equations, based first in the original Griffiths theory that was part of his PhD thesis, as John Harrison has commented, and also in the modification of the Griffiths theory by McClintock and Walsh, based on the frictional forces in the joints. And then they start to compare strength results to different possible failure criteria. And he refers that in deriving their empirical failure criterion, in this case looking for intact rock, the approach was one of pure trial and error. So basically based in a lot of test results on different rock samples and the normalized representation that Professor Harrison has mentioned. They just choose the criterion they use over the many alternatives, just lighting the good predictions and convenient application to typical rock engineering problems. So, at the time, during the 60s, many people were doing testing in the labs, and this is an example of Richard Wieniawski, where, the more envelopes for strength failure criteria follow a non-linear, let's say, non-linear trend. No? This is for the fracture initiation that can be a little bit more straight line. And those are pictures for the book in 1980, and I'm talking now about intact rock. And we can see that they obtained very good fits to this type of parabolic curve. But then, they have to move to the rock mass. And this is something, at some point also of my career, we decided to do this test on jointed using rock. So that's why at some point I review all these nice papers, and I do love the result they were obtaining at the time and the way in thinking. So a number of researchers do this small test using typically an engineered material plaster with, this is Brown and Trollope, 1970, in unjointed material, and this same material with two joints with different orientations. So they first look at the failure mechanism. So of course, depending on the type of rock and the angle of jointing, you can see here the most relevant mechanisms they were observing. But, as Dr. Hoek states, since there are a large number of possible combinations of block shapes and size, it's obviously necessary to find the behavioral trends which are common to all these combinations. So they were looking for a particular type of equation that could, take into account all these possible problems. This is the representation of the results of these different tests. So basically, they realized that, they're noticeably curved in all, so a linear strength law may not be applicable, as we've said before. And he also saw that for both the jointed and unjointed samples, they need a power law, and the systems can behave in a very different manner according to the presence of joints and to the orientations of these joints. This was a paper by Branko Ladanji, and Guy Archambault in the 70s that they were trying to also answer this question of how's the strength of this material. So they started to in some way bracket the problem, trying to do in these very simple models with small concrete blocks. And based on the evolution of dilation and the shear parts, they kind of bracket the behavior of this between just friction sliding in a planar joint. This will be that of the intact rock, and they can identify some different strength failure criteria for irregular rock surface, for fissure rock, and for what they understand as a rock mass. And this has an empirical background, so it was based in the test they were doing. Also, Professor Einstein and one of I think his PhD student, they make a lot of tests with different orientations of these jointed materials, and came to similar conclusions. So trying to focus the rock mass strength. They saw that sliding along joints can be like a lower bound. The intact material can be an upper bound. And they also resort to the Griffith line and see how different levels of jointing produce a slightly different strength strength responses. And also, as John has presented in the first studies, Hoek resort to this Jaeger plane of weakness behavior that we can obtain when testing an isotropic rock or testing a sample with just one joint. So those are figures from some authors, McLamore and Gray and Horino and Ellickson on different anisotropic rocks. And we've done also this type of test in roofing slates in our area to obtain also some similar results. Those are results for I think it's Delabole Quarry in UK. So we have this kind of trends, but he realized also based in this paper written in French by Ladangi and Archambault that, first you can obtain different mechanisms, but what was more interesting is that if we take into account the presence of two joints with two different orientations, theoretically, and based on these Jaeger planes of weakness, we should have this theoretical response for different confinement levels. But what we see in practice is some, kind of more fuzzy response, so some more going through anisotropic behavior. And this is one wonderful research study of Professor Klaus Werner John from Karlsruhe, and they do also this test, and he make these same representations, but they represent the results just according to the strength in every direction according to the joints. So he realizes that when two of these U-shaped anisotropic strength response get together, so he tried to overlap this and looking for curves representing this behavior. So that was kind of the theoretical approach, and here, similar to what Dr. Evert Hoek do a few years before, he represented all the results of all the samples, and he checked that the theoretical response were reasonably matched by the observations in the lab. So if we consider a rock sample with two joints with different orientation, and we represent the strength behavior in all possible directions, so we will obtain this kind of strength response for one joint for the other. So in general, we will have this blue one. So there's a trend to isotropization. So we can go to a strength that's representative of the rock mass. And those are the graphs that Evert Hoek present in their book of 1980, where when we have like three joints with, let's say 60-degree orientation, we can compute strength results that can be in some way, isotropic. So I think when he was proposing his final strength criterion, he has in mind this kind of response that this can be in some way more representative of a rock mass containing, at least 4 or more such joint sets. This is another paper from Ted Brown, also in the 70s, with strength models of rock joints in intermittent joints. So he prepared also these engineered samples with different kind of jointing. So we can see here the results in terms of shear stress, normal stress in more circles. He identified, this will be the case for the unjointed rock. He identified that this was the weakest point, so he kind of identified the lower possible strength. This was the strongest one that appear here. So they kind of look to the joint rock strength rates to try to bracket this. And in this particular paper, observing the response and where every joint was broken, he tried to compute the strength of this, taking into account the part broken through intact material and that occurring through joints. So, at this point, Ted Brown proposed this formula, and he compared the calculated results with the one measured based on their test with a, reasonably good approach. Of course, not perfectly accurate. So I think also this idea was behind the proposal of the failure criterion, which probably the final equation was based in these results of tests on Panguna andesite under different conditions. So I understand Dr. Evert Hoek followed these projects for 20 years, so they have a good number of tests on this intact andesite rock, but also results in undisturbed cores, recompacted samples, fresh to weather samples, moderately weather samples, and highly weather. So he rated this as, well, kind of rock mass using two types of classification, this CSIR classification, which was, well, similar to RMR, and also the NGI quality index Q. So, well, based on that, he was able to, like, fine-tune their equation to eventually, well, propose the well-known failure criteria. So this is representation of M and S values in relation to the rock mass classification approach. So, well, this is where I want to come in this part. In 1980, well, they proposed the formulation in their book, then they use RMR, no? They resort to RMR, and later on to GSI, and you know the rest of the story because Professor Vassilis Marinos has explained in good detail. But I mean, in some way, if you were an engineer in the 60s, you don't know how to estimate the strength of rock. So you have no idea now. I mean, it's very easy at least to have some orientative values that you can start to play with. And of course, you have to look at a number of other things to make sure that this will work. But in some way, the foundational ISRM problem of what is the rock mass, the strength of a rock mass have been solved for that. So that's why we are well happy to honor Dr. Evert Hoek, and it was well an incredible achievement. Yeah. This is, well, kind of the same letter response of Evert Hoek that John Harrison has commented before, and well, you can well read what Dr. Hoek saying about their own well criterion. So, I mean, I highlighted that because I think it's interesting. So he said that to propose their criterion, and probably the data I have shown was the base of that, but they work on very limited data of rather poor quality. And, well, in fact, he was taken aback of how it has been, or his criterion was applied to a lot of different situations, you know, using, and I mean, still we have not probably moved forward much using the same estimates that were made 15 years ago and now 35 years ago. So yeah, I mean, I recommend you to read that. It's kind of very interesting. And we have here also, well, Dr. Hoek, that was in 1991, given a presentation in the official day of the Spanish group of the Rock Mechanics Society. So yeah, he was a very kind man, always ready to help and to explain things. And I was one of the people that was sending him mails, and he answered me. So I'm also personally acknowledged for that. And well, I mean, if I presented all this data, is because, well, at some point, as I've said, we have done a lot of tests, mostly focusing to understand post-failure behavior in our laboratory with, in this case, we use jointed granite. So I have a very skillful student that was able to do these very nice samples with different number of joints. And well, you can see the kind of response of intact, slightly jointed and highly jointed rock, and we can see perfectly how the trends of decreasing strength, decreasing deformability, and also decreasing dilation trends can be observed in line with the appreciation of Dr. Hoek and Brown. So that's the end of the first part of my talk, and I will move to the practical rock engineering approaches. So to introduce that, I'm going to tell you a little story. My PhD thesis supervisor was Professor Ramírez Ollanguren from the School of Mines of Madrid. And in 1966, he was working for a mine, so he was invited to follow a master program in Newcastle in England. And this master program was led by Professor Potts, who I think he was a specialist in this kind of observational approach. So well, he went there when he finished his master thesis, and he told me, this professor, about the conversation with Dr. Potts. We were in 1968, and Dr. Potts says, oh, you know this hippie, these flower power people from the Imperial College in London, they do wonderful mathematical things. Yeah? You see the results and the slides or how it looks like, and well, this is really nice. But the problem with them is that when you go to a mine and a pillar is failing and you have a problem in the tunnel phase, they don't know how to do. So that was, I mean, the view of the rock mechanics were at that time, and I think he was right. And I bring this story here because I think that probably the most relevant individual that has made that all these mathematical approaches or numerical approaches can be used in daily life engineering, that's Dr. Evert Hoek, and that's why we honor him here today. And well, to comment briefly some of the most relevant contributions, probably not the most relevant, but the ones that I have been of more help to me, I will just comment, well, these three short topics presented in his book, in Practical Rock Engineering. So when is a rock engineering design acceptable? This was, in fact, based on a talk of Dr. Hoek when he received the first Mueller Award. So that was the most relevant award of the ISRM. I will briefly talk of the analysis of rockfall hazards. And another example I used to present to my students to understand how things work or how to take a formula and full it of real engineering sense. So I will briefly comment these three cases. So in his chapter, when is rock engineering design acceptable? Well, he starts that stating that there's no unique factor of safety or probability of failure or number that can be useful in every case. So the important thing is look to every structure, to every problem based on its own merits. So at the end, also, of course, the responsibility, it's in the engineer. So he presented the number of typical problems in rock mechanics, for instance, landslide. And in this well, wonderful table, he presented the typical problems, the critical parameters, their analysis methods, and the acceptability criteria. So to present an example, for instance, in jointed rock slope, typical problems are planar or wedge failure with a structural control. The critical parameters are the geometry of the slope and, well, the geometry of the joints, groundwater, earthquake, and sequence of excavation. So he explains you possible problems, what you have to look particularly at. So, of course, the depth of potential planar failure joints is much more important than density, so spend your money there. They give you also what kind of methods you should use, so limit equilibrium analysis or three-dimensional one. If the problem is more 3D type, you can use failure probability analysis, well, based also on statistical distributions. And he gives you the acceptability criteria. So in this case, maybe 1.3 for a mining slope, 1.5 for a civil engineering slope, some time of probability of failure. So he gives you the keys to focus this problem from, well, a lot of different typical cases. So in my life, 2 or 3 times, I came across new problems, and just looking at that, I mean, just after reading these, well, simple ideas, you have a more clear idea of the focus or what you should look at when analyzing a particular rock engineering problem. Okay, one of these problems was the analysis of, well, rockfall hazards. And you can see, well, here are the kind of problems that are expected, the critical parameters, the analytical methods, and acceptability criteria. In this chapter, he also presents this rockfall hazard rating system which is a kind of checklist. We're looking at, well, it's kind of classification system that can be of help to first look at a problem and identify what potential issues can be there. And also he presented this nice event tree analysis for rockfall hazard, where based on more or less reliable information, one can provide probabilities of the different sub-events or individual events to get to basically annual probability of occurrence. So if you can compute that, also finally he provided some levels of acceptable risk. And one of the few times I've been talking with Dr. Hoek, I remember that we were talking about what risk is acceptable. And he said, if you ask any politician, he said 0. But we all know that, I mean, there's always some great risk at stake. So in some way, the engineer has to make his mind out or look for some reference that can be applicable. So, well, I also presented this because based on this proposal, at some time we realized that in Spain, the records of accidents in quarries due to rockfall were very high. So using these, well, simple approaches, we, finally proposed a kind of very simple charts that can help you to design which is the appropriate catch bench that you should use in a particular quarry, taking into account backbreak and so on. So it's a very simple approach, but I'm aware that it's used by, well, some companies in the field of aggregate quarries in Spain and in some other countries. And the last problem I want to, well, recall here, it's this slope stability problem in Hong Kong, where, well, he proposes this well-known formula to analyze planar failure based on the forces acting on the case. But I really learned a lot reading that for the first time, and as I told you, I use it with my students because, well, the first thing he does, I mean, he kind of put a full sense on it. So how can we use this formula? Okay, so let's think factor of safety is 1, so let's represent the values of C and A for the different possibilities available. So, I mean, for every one of these possibilities, that can be, well, only the bench or the whole slope, occurrence of a tension crack or not, saturation not. So we have these, well, different lines. And so if the strength is below this line, we have problems. It's over this line, we don't have problems. So that means that 6 out of 7 cases, that's not a problem. And the only possible problems would be if we have a saturation condition together with an earthquake, and you can check if this kind of situations were possible to occur in this slope in Hong Kong at the time. And then using this simple formula again, he analyzed how changing the different potential input parameters in terms of, well, geometry, but you can use it also in terms of anchors and so on. You can move the factor of safety to a level that it's acceptable for you. So, well, all in all, in this case, well, the option finally chosen was to reduce the slope face angle, just cutting down to 35, so basically removing all this big wedge. And in fact, well, they proposed to do that, and they do it, and they use the money they recall to pay in some way the stats there. And they don't have data at all in the beginning. He also, well, recommended at some point to make some tests. But I mean, I've been often in this kind of situation, so they call you from a quarry, said, Leandro, we have this problem, what can we do? So, I mean, you have no information at all, so try to start with this kind of approaches. I think it's a kind of a good idea. So I will end this part of my talk with a quotation that I use often, that was in the preface, in the foreword of the Hoek and Bray book. And they said that because the rock mass behind every slope is unique, there are no standard recipes or routine solutions which are guaranteed to produce the right answer each time they are applied. So for the sake of rigorousness, I present here the references I've used to present that. And, well, do we know the strength of the rock? Yeah, for intact rock, yes. But for rock mass, probably not. So that's why we are here today. But yeah, thank you to Dr. Hoek to help us to solve, at least in the first level or in the first approach, this problem, and why he's probably the first Mueller Award recipient in our society. So thank you for your kind attention.
Thank you very much, Professor Alejano. This was a very nice presentation of the rock mechanical and rock engineering aspects of Dr. Hoek's work. Is there one or two comments, perhaps? Otherwise, I would say we can close this part. So thank you very much, Leandro. Thank you very much also to John Harrison and to Vassilis Marinos for their contributions. And yeah, then I would say let us close this scientific farewell for Dr. Evert Hoek here at the first International Rock Mass Classification Conference in Oslo. So everybody who is eventually watching this in the future, goodbye from our side.